We will now start discussing differential and integral operations on vector and scalar fields. So let's start with what is a field. It's a function of position and time, and we have two classes of fields, scalar fields and vector fields. Scalar fields only have magnitude. A good example is potential distribution, charge density, temperature, and pressure. And on the other hand, vector fields have both magnitude and direction. For example, electric field, current density, gravity, and fluid velocity. So let's start with scalar fields. As an example, consider the electric potential phi produced by two parallel uniform line charges of charge density plus or minus lambda 0 located at x equals plus minus 1 and y is equal to 0. So that is to say, we have positive charge here, negative charge here, plus lambda 0 minus lambda 0. Uniform line charge and located at x equals plus 1 and minus 1. So z-axis is coming out here and we're looking at the potential at a certain point which is a distance x from the origin and y on the y-axis. So in order to calculate the potential distribution due to this setup, we're going to first use Gauss' law to calculate the electric field due to an infinite line of charge. So let's think about a line of charge going through this region, and we can draw a Gaussian surface around it, which is going to be cylindrical surface that's coaxial with this line of charge. And if we look at the electric field lines coming out of this, they will be perpendicular to the surface. So electric field would be normal to the surface like this at any point. So if I am at a radial distance here, they would be perpendicular to the surface, for example. And if the cylinder has length L, we can write Gauss' law. The closed surface integral E dot dA, the total electric flux, is equal to charge enclosed divided by epsilon 0. Charge inside divided by epsilon 0. Now, since the electric field is only a function of r, the radial distance from the center, and it's perpendicular to the surface here, we're going to have the surface vector parallel to the area. The surface area vector will be parallel to the electric field lines because it's the normal vector, and we will have electric field times the surface area. What's the surface area of the cylinder? 2 pi r times L. So E times 2 pi r L, L is the length of the cylinder, is equal to the charge enclosed, which is the linear charge density lambda times the length L divided by epsilon 0. So this tells us that the electric field can be written as, now noting that we have Coulomb's constant K is equal to 1 over 4 pi epsilon 0. This can be written as 2k lambda over r, 2k lambda r, radial distance from the center, in r hat direction. So that's our electric field that's emanating from this surface. Then we want to calculate the potential due to an infinite line of charge using our electric field potential relationship. Electric field is minus the gradient of the potential. So if I go from a point R to point R0, the potential difference would be the integral R0 to R, electric field dot product with dl. So it's this path integral. Now, basically, this is my R0 that I'm considering here is my reference point where I will take the potential to be 0. So I will, it's approximately infinity over R. And then I have 2k lambda over R, my electric field, dr. Okay. And this is going to give me, basically, I'm taking R0 to be approximately equal to infinity. This is going to give me 2k lambda natural logarithm R over R0. And that is basically the potential at R0 minus the potential at R because of the minus sign in the gradient here, minus gradient of V. So if you go from R to R0, that is, if you, this is your initial potential, this is your final potential going from position R to R0, that would be minus the integral R to R0 E dot dl, but because the minus sign would change the order of the integration limits, it is R0 to R. So instead of taking the potential to be 0 at infinity, we are actually taking to be 0 at R0, an arbitrary reference point that we choose, a radial distance R0. We have 0 potential. So this is our choice. Okay, so basically I am replacing normally what I would have at infinity with R0 here for this potential in order not to have it blow up. Okay, so this tells me that the potential distribution as a function of R is given by 2k lambda natural logarithm R0 divided by R. So notice that I have switched from R over R0 to R0 over R because of this minus sign here. And that tells me that I can use this result to calculate the potential at point P. The potential at point P is due to the positive line charge and the negative line charge. Now, what is my radial distance for the positive line charge? It is x minus 1 square plus y square square root. That's the radial distance. So you consider this right triangle here. So that means for that part of the charge distribution, I can write 2k lambda 0 natural logarithm R0 divided by x minus 1 square plus y square square root. All right, and the contribution from the negative charge, that's this part, will be x plus 1 square plus y square square root for the radial distance. So this will give me a minus 2k lambda 0 natural logarithm R0 divided by x plus 1 square, that's the radial distance, plus y square square root. So that gives me the total potential at point P. Now, if I put this in 2k lambda 0 parentheses, I was showing the potential at point P with phi. So phi at point P is 2k lambda 0 natural logarithm. Now I have this divided by this, so this is going to go upstairs. R zeros will cancel. So I will have x plus 1 square plus y square square root divided by x minus 1 square plus y square square root. And that means I have the square, everything under the square root here. So that means I can take the square root out of the natural logarithm as 1 over 2. It's to the power 1 over 2. So this 2k lambda 0 becomes k lambda 0. And I have inside the natural logarithm x plus 1 square plus y square divided by x minus 1 square plus y square. So that's my potential distribution. Now, I can plot this potential distribution using any plotting software, and here I have used Mathematica 14. So you can see that I have defined that this is natural logarithm, x plus 1 squared plus y squared divided by x minus 1 squared plus y squared. That's multiplied by a constant, that doesn't matter. So we can do a contour plot of this, and then we can take the gradient of the scalar field minus the gradient to show the electric field associated with it. So that's the result of this code. You can see that the scalar field phi has a minimum value close to the negative charge here. It has a maximum value close to the positive charge here, and electric field lines point from the positive to the negative charge distribution like this, and the magnitude of the electric field drops off as we go farther away, as we increase the radial distance from the center, and it has the highest magnitude. The strongest electric field lines occur when we are close to these lines. So that's in between these lines. And actually, the electric field strength is shown in this plot using the color scale, as you can see. Normally, by convention, we plot actually electric field lines so that they have a high density where the intensity is high, and low density when the intensity is low. So that's one way of drawing the electric field lines. And instead of doing it this way, basically, I have drawn the electric field lines using this color scale. So the color scale shows me where the intensity is decreasing, in which region of the space the intensity is high, and in which region of the space the intensity is low. Okay, so as a summary, we have talked about fields. We have scalar fields and vector fields. We note that scalar fields have magnitude, and potential is one example. So as an example, a demonstration of plotting of a scalar field, I've considered the electric potential produced by two parallel uniform lines of charge density lambda 0 plus or minus lambda 0. First, I have used Gauss law to find, I've drawn a Gaussian cylinder here to find the electric field due to such a charge distribution, and then calculate the potential due to a uniform line of charge, and that gives me 2k lambda natural logarithm r0 over r if I take the potential to be 0 at a reference radial distance r0. And I can calculate the potential at point B by replacing lambda with lambda 0 and noting that I have a positive and a negative contribution, and the radial distances for this contribution is square root of x minus 1 square plus y square, and for this contribution square root of x plus 1 square plus y square. That's the radial distance, and I can calculate the total potential at point B this way. So that's my end result for this calculation. So that's the potential distribution. Now forget about k and lambda 0. We can just plot this function as a function of x and y. So I've used this Mathematica 14 code in order to plot this. A contour plot shows the scalar field, and the vector plot shows the electric field associated with it, as you can see here, where the color scale indicates the magnitude. So it's basically high intensity electric fields close to the lines of charge here, and when I go radially far away, the strength of the electric field drops and the potential increases as I go from left to the right towards the positive charge distribution. And this is not the conventional way of drawing the electric field lines. The conventional way is basically showing a high intensity of lines, densely packed lines in the regions of high intensity, and also sparsely packed lines when we are further away from the center here, where the electric field strength is much weaker.